Hello friends, welcome to engineering tutorial. So today we are going to discuss about some more network theorems. We have already discussed about superposition theorem and Thevenin's theorem for both circuits involving independent and dependent sources. So now we are going to discuss about the next important circuit theorem, which is Norton's theorem. So first we'll discuss the basic statement and some basic concepts related to its application, and then we'll solve some problems, some questions, so that we understand it in a good way. So like Thevenin theorem, Norton's theorem is also, its basic application is related to simplifying a large and complicated circuit, linear and bilateral circuit, into a simple form. Okay, so let us say we have a circuit. Okay, it can be consisting of multiple voltage sources, current sources, resistors, like this. Let's say we have this circuit here, and we want to find the Norton equivalent circuit across these two terminals. Okay, so for that, according to Norton's theorem, we can convert this circuit into this simple form, that is a current source in parallel with the equivalent resistance, the Norton equivalent resistance. So in Thevenin theorem, it was the Thevenin voltage in series with the Thevenin equivalent resistance. Here we have the Norton current in parallel with the Norton equivalent resistance. Okay, so the basic statement of Norton's theorem, it says that any linear bilateral DC network containing more than one energy source, be it voltage or current source, it can be replaced with its equivalent circuit consisting of a current source in parallel with a resistance. So that current is called as the Norton current, and the resistance is called as the Norton equivalent resistance. So like we did in the Thevenin equivalent circuit, it consisted of two parts. First, determination of Thevenin voltage, second, determination of Thevenin resistance. So here also it consists of two parts. First, determination of the Norton current, second, determination of Norton equivalent resistance. So to determine the Norton current, what we have to do, let us say we have this circuit here, we have this circuit, and we have to determine Norton equivalent across these two terminals. So in order to do that, first what we have to do is we have to short circuit these two terminals 1 and 2, across which we have to determine the equivalent circuit, the Norton equivalent circuit. And that current flowing through this short circuited path, that is called as the Norton current. Okay, so we have this circuit, we have to determine the Norton equivalent across these two terminals 1 and 2. So first step, short circuit them, find the current flowing through the short circuited path. All the sources, independent or dependent, they should be intact, they should be considered. Find the current, that is the Norton current. That is the first part done. Okay, so we have got IN. Then Norton equivalent resistance. So the determination of Norton equivalent resistance is the same as we did in Thevenin equivalent resistance. Norton equivalent resistance and Thevenin equivalent resistance, they are the same. Rn is equal to Rth. So here also, to determine the Norton equivalent resistance, we will first deactivate the independent sources. So we will short circuited the independent voltage source and open circuited the independent current source. So here there is no dependent source, so no confusion about that. So we simply short circuited the voltage source, open circuited the independent current source, and determined the equivalent resistance, which is R1 parallel to R2 here in this case. So that is the Norton equivalent resistance. The same things we did in Thevenin equivalent circuit also. So Thevenin equivalent resistance determination and Norton equivalent resistance determination, they are the same. The procedure is the same. It is the same. Okay, resistance, equivalent resistance is the same. Just in Thevenin equivalent circuit we call it the Thevenin resistance, and in Norton equivalent circuit we call it Norton resistance, but they are the same. RTH and RN are the same. The procedure of determination is same. So now we have got both IN and RN. So the next step is to draw the Norton equivalent circuit, which is simply the Norton current in parallel. We have the Norton equivalent resistance across the terminals 1 and 2. So this is the Norton equivalent circuit. Okay, so this is only for circuits involving independent sources. So as we know, voltage and current sources are of two types, independent and dependent. So we always solve problems, be it for superposition or Thevenin, for in two cases. First, circuits involving independent sources, then dependent sources. So don't worry, I will be solving problems related to both independent and dependent sources, how to handle them. So like we did in superposition and Thevenin, so here also we'll do in the same way. So independent voltage sources are simply short circuited, independent current sources are simply open circuited for determination of the Norton equivalent resistance. But when there is dependent voltage sources, things are handled in a little bit different way, which we already know in Thevenin's theorem. So we will be doing the same in Norton's theorem also. So we will be solving some questions. So now let us understand the application of Norton's theorem by solving some questions. So we will be solving a lot of questions related to Norton's theorem. Don't worry about that. So we just studied the statement of Norton's theorem, and what basically we understood is that if we have any circuit, okay, any electrical circuit, okay, let's draw a circuit. Okay, voltage, 3 resistors, let's say, or any circuit involving any number of voltage source, current source, resistors. If we want to determine the Norton equivalent circuit, what we have to do first, in order to determine the Norton current, we have to short it first, then we have to find this current, which is the Norton current. Okay, then we have to determine the equivalent circuit, which is the same thing that we did in Thevenin equivalent circuit. Okay, so Norton resistance, equivalent resistance, is the same as Thevenin equivalent resistance. Okay, it is the same. So for doing that, what we have to do, we have to open circuit the current sources and short circuit the voltage sources, okay, and find the Norton's resistance, which is the same as the Thevenin resistance, the equivalent resistance across these 2 points. So this is basically what Norton equivalent circuit means, and these 2 points, across these 2 points, the Norton equivalent circuit will look something like this. The Norton current and the equivalent resistance connected in parallel across it. This is the Norton equivalent circuit. Okay, In a Thevenin equivalent circuit, we used to calculate the Thevenin voltage and the equivalent resistance was connected in series. Okay, this is Rn, which is the same. So here this is the Norton equivalent circuit. This is the Thevenin equivalent circuit. Okay, so this is basically what the Norton equivalent circuit determination essentially is. Okay, so let us solve some questions to understand this concept in a good way. Okay, so this is the first question which we are going to discuss related to application of Norton's theorem. So this is the circuit here. It has this 2 ampere current source, 12 volt voltage source, 4 ohm, 8 ohm and 8 ohm resistors and this 5 ohm resistor, and we have to determine the Norton's equivalent circuit across the points A and B. So it consists of two parts. First we have to determine the Norton's current and then the equivalent resistance, deactivating the independent sources. So here it involves only independent sources. So let us start. So first we have to redraw the circuit, short circuiting these two terminals. Okay, so let us redraw the circuit. Okay, and we will short circuit these two terminals. Okay, this is 2 ampere, this is 8 ohm, this is 8 ohm, this is 12 volt, this is 4 ohm, this is 5 ohm, and this current is the Norton's current. Now when we short circuit these two terminals, what happens is that this resistor connected in parallel across the shorted path, it goes out of the circuit because it makes no sense, because the equivalent resistance will be 0, because short circuit is 0, resistance is 0, so it goes out. The 5 ohm resistor goes out. Okay, so now we have to determine this current, the Norton's current. Okay, so let us apply KVL in this loop. Okay, we will apply KVL. So here the current flowing is 2 ampere and here it is IN. So here the current flowing will be 2 minus IN in this branch. In this branch 2 minus IN. Okay, 2 ampere, IN going here, so it will be 2 minus IN. So now let us apply KVL in this closed loop. So it will be, let us start, it is 12 starting from here. The voltage polarity will be like this, always pay attention to that, because the current is flowing in this direction, 2 minus IN, and IN here is flowing in this direction, so the polarity will be like this. Here also it is flowing in this direction, so the polarity will be like this, because current always flows from positive to negative terminal through a resistor. So the KVL will be 12 plus 4 into 2 minus IN minus 8 IN minus 8 IN is equal to 0. Okay, next 12 plus 8 minus 4 IN minus 8In minus 8In is equal to 0. That implies 20 minus 20In is equal to 0. That implies In is equal to 20 by 20, which is equal to, it is in volt and ampere, so it will be 1 ampere. So In is equal to 1 ampere. That is the first step, that is complete. We have got In. Now we have to determine the equivalent resistance across these 2 points, deactivating the independent sources. So we have calculated the Norton current, which was In is equal to 1 ampere. So now we have to determine the Norton resistance or the equivalent resistance across these 2 points. So this is the same procedure we will follow as we did in Thevenin equivalent circuit. So we have to determine this resistance deactivating the independent sources. So for that we have to open circuit the current source and short circuit the voltage source. Okay, so this 12 volt voltage source is short circuited and this 2 ampere current source is open circuited. So now the Norton equivalent resistance, the equivalent resistance here is 8 plus 4 plus 8, these 3 are in series, so it is 8 plus 4 plus 8, and this combination of these 3 resistors is in parallel with 5 ohm, so that is 5. So it is 20 parallel 5, which is equal to 25 by 20 plus 5, which is 25, which is 100 by 25, which is 4 ohm. So the Norton equivalent circuit, the equivalent circuit resistance across these 2 points, Rn is 4 ohm. So the Norton equivalent circuit is this is 4 ohm, this is 1 ampere. So this is the Norton equivalent circuit across these 2 points for this circuit. Okay, so this is the first question which we have solved related to the application of Norton's theorem to circuits, electrical circuits. Okay.